Welcome. On this video, we're going to be discussing how to solve rational inequalities. So let's get started. Right here on the right hand side, we have the procedure that we'll be using to properly solve rational inequalities. So let's take it one step at a time and let's show it in some examples. So here we have the following. So here we have a rational expression, and notice that there is no equal sign involved anymore. Now we have an inequality. So now we want to show when is it, or under what x values, is the whole rational expression always going to be greater than 0. So for any rational expressions or equations or inequalities, we always want to make sure that we're working with the simplest rational expression. So notice that in the first example, there is nothing else that we can do to simplify just the rational expression. So step number 1 is done. Now what we want to do is we want to set the inequality equal to 0. So let's do that. We're going to have x minus 1 over x plus 2, and we're just going to set it equal to 0. So step number 2, it is done. So now here's the most important step. We want to find the zeros of the numerator and denominator. And this is why we wanted to set it equal to 0 first, because we want to kind of ignore the inequality for a second and just treat it like if it was an equation now. So I'm going to set the numerator equal to 0 and set the denominator equal to 0. And let's see what happens. Well, for the numerator, we're going to have x minus 1 equal to 0. And for the denominator, we're going to have x plus 2 equal to 0. So let's solve it. So for the first one, I'm going to get a solution of positive 1. And for the second one, I'm going to get a solution of negative 2. So we're done with step number 3. Now, we're going to be testing some solutions. So what do we mean by that? Well, let's create some kind of a number line here. So here, I'm just going to assume that this is a number line. And I'm going to be placing in this number line the values that make my numerator and my denominator equal to 0. So let me just place negative 2 right here. And let me place positive 1 about here. Now, to test the solutions, we want to see if it will give me a true statement. So I know that if I use positive 1 as a value of x and I plug it into the whole rational, I'm going to have 0 in the numerator and some expression in the denominator. So the whole rational is equivalent to 0. So now, is 0 greater than 0? Well, that is false. If my inequality would have been written as less than or equal to 0, then that would have been a true statement. So since we're only working with just greater than, so I'm not going to be taking 1 in consideration as my solution. So what I'm going to do in the number line, I'm just going to create a hole at positive 1, because I know that positive 1, it is not part of my solution set, because if I plug it in, it gets me 0, and 0 is not greater than 0. So now let's check negative 2. So if I plug in negative 2, my denominator is 0. So that's an undefined value. So therefore, I don't want to use it as my solution, as being part of my solution set. So I'm just going to create another hole at negative 2. So that's what we mean by testing solution. Take a look at what you have and see if it gives you a true statement under the original problem. So now that we have tested solution, notice that by plugging in those two values in this number line, we have created three intervals, from negative infinity to negative 2, from negative 2 to 1, and from 1 to positive infinity. So let me just label them. Let me call I1 to be the interval from negative infinity to negative 2, I2 from negative 2 to positive 1, and I3 from 1 to positive infinity. What I want to do now is I want to test the intervals. So let's concentrate on the interval from negative infinity to negative 2. What I'm going to do to test this interval is I'm just going to be choosing a point in this interval. So any value that is less than negative 2, it will be part of this interval. So I'm just going to be choosing the value x equals negative 5. And I want to see what happens when I plug in this value, a value on this interval, in the original statement. Am I going to get a true or false statement? Well, let's see. So let's just plug that in there. So we're going to have -5 and -5. Now, we're claiming that this is greater than 0. Well, let's see if that is true. If we simplify this now, we're going to get -6 on the top and -3 on the bottom, greater than 0. So now we're going to get -6 divided by -3, so that's 2 greater than 0. And now we ask ourselves, is this a true statement? Is 2 greater than 0? Well, this is true. So therefore, I am going to be taking in consideration this interval. So the interval from -infinity to -2, it is going to be an interval that will give me true statements. So therefore, I'm going to take it in consideration in my solution set. So now that I have tested the first interval, let me test the second interval, where again, the second interval, let me call it I2, it is the interval from -2 to +1. So choose any value that is between -2 and +1. I'm going to be choosing the easiest of them all, which is 0. So what happens when x is 0? Let me plug it into the original statement that we had here, and see if it's true. So now we're going to get, let me just plug that in real quick here. So let me just plug in 0 in red so you know where it's coming from. And now we're saying that this is strictly greater than 0. Well, let's simplify this. -1 divided by 2 greater than 0. Is -1/2 greater than 2? Well, this is definitely false. Well, since this statement, it is false, and I use a value on the second interval, then I'm not going to take in consideration the second interval as being part of my solution set, because it fell the original statement. So now that I have that, I'm going to be testing the next interval. Let's test the interval I3, which is the interval from 1 to +infinity. Let's choose a value that is in that interval. Again, you can choose any value. So for I3, I can choose 2, 3, 4, 5. Just going to make sure that it's a value in this interval. So I'm going to be choosing x equals 3. So it's going to be somewhere here. So I'm going to be choosing x equals 3. So let's plug it into the original statement. So we're going to have -1 plus 2. So we're going to have 3 here, 3 here, greater than 0. And let's simplify and let's see if it gives me a true statement. So now we're going to have 3 minus 1, so that's 2. 3 plus 2, so that's 5, greater than 0. Now is 2 over 5 greater than 0? This is a true statement. So therefore, I'm going to be taking in consideration this interval as being part of my solution. So if notice that the only two intervals that gave me a true statement are the first interval and the third interval. So therefore, that is my solution set. Now my solution, it is not just a value. My solution is a combination of the intervals that give me a true statement. So my solution are the interval from -infinity to -2, and I'm going to be jumping the second interval. So I'm not going to take any values between -2 to +1. And now I'm going to unionize it, and from 1 to +infinity. So now this is my solution for this rational inequality. Any value that is between these intervals will give me a true statement. Therefore, it is a solution. Now let's take a look at another example. So here we have example B. Again, the first step is, let me make the whole inequality into an equality. So there it is. And now the second step is, what value makes my numerator equal to 0 and my denominator equal to 0? Well, for the numerator, let's see, 1 minus x equals 0. So we got -x equals -1. So x is equivalent to 1. So actually, I just recognized my mistake, because notice that this is actually simpler, if that's even a word, than what are the steps that we took previously. Because notice that under my denominator, it's a single value. So I can just get rid of this rational and just work with a linear equation. How do I do that? Well, what happens if I multiply -2 to both sides? So if I multiply -2 to both sides, this -2 is going to cancel out with this -2. So now I have 1 minus x. But remember that when you multiply, you have to switch the direction of the inequality. So now it's facing to the right. And 7 times -2, that's -14. And now this becomes just a regular inequality that we have solved previously. So let's solve for that x. So we can just skip all the steps that we did previously. So -1. So now I have minus x greater than -15. Let's divide it by -1. So the sign cancels out. And remember that when either you multiply or divide by a negative value, the sign is to switch. So it is facing to the right. Now it must be facing to the left. And that's equivalent to 15. So let's just represent this statement in some kind of a number line. So here we have our number line. Here I have the value of 15. And I'm saying I'm going to choose all those x's that are less than 15. But notice that we're not including 15. So 15 is going to have some kind of an open value. And I'm just going to be choosing those that are on the left-hand side of it. So therefore, this is the only interval that we had information on. So therefore, my solution is just that interval. So my solution is the interval from -infinity all the way to +15, open parentheses, because we cannot include the value of 15 since we don't have a less than or equal to. We just have a less than statement. So therefore, 15, it is an open value. So let's take a look at the last example. So under the last example, you will realize one thing, and that is that now we're working with two rational expressions. So how can we solve this? Because so far, all we have dealt with is whenever we just have one rational expression. So how can we do it if we have two rational expressions? Well, I'm going to try to rewrite all this in one single rational expression. So how can I do that? Well, first, let me bring this expression all to the left hand side. So -4 over x minus 2. That way this cancels out. So now I have my new expression as 5 over x minus 3 minus 4 divided by x minus 2 greater or equal to 0. And I said that right now my goal is to rewrite this whole expression, or here I have two rationals, so I want to rewrite it as a single expression. So how can I do that? Well, just like we did with solving rational equations, I'm going to look for the LCD. Notice that we have two different expressions, x minus 3 and x minus 2. So therefore, my LCD is x minus 3 times x minus 2. And now what I want to do here, I want to make sure that every single denominator has that expression. So if I take a look at my first rational expression, I have x minus 3. So what I'm missing from the LCD is x minus 2. So let me multiply x minus 2 on the top and x minus 2 on the bottom. And now let's move on to my next expression, 4 divided by x minus 2. In this denominator, I have x minus 2, so the expression that I'm missing is x minus 3. So therefore, let me multiply x minus 3 on the top and x minus 3 on the bottom. And by doing that, let's rewrite our expression now. So this is going to get distributed. So now I have 5x minus 10. Now my denominator is x minus 3 times x minus 2 minus, let's distribute this and this. So now it becomes 4x minus 3. Now my denominator is x minus 3 times x minus 2, still greater than or equal to 0. Now that I have the same denominator on both of them, I can definitely combine the numerators. So now this is going to become 5x minus 10. Be careful with this negative, because this negative is affecting the whole fraction. Therefore, it is going to change the sign for those two terms. So now that is minus 4x plus 3. And my denominator, it is still the LCD, x minus 3 times x minus 2 greater or equal to 0. So let's just simplify this a little bit further. I can combine like terms. 5x minus 4x, that is 1x, negative 10 plus 10, negative 10 plus 3, that's definitely minus 7, divided by x minus 3 and x minus 2. And now notice that all we have done is we rewrote the original inequality, which it was written in two rational expressions. All we have done is we wrote it as a single expression. So now I can kind of ignore this and just work with this. And now that I have it in this form, now we can do the procedure that we stated previously. So let's do that procedure. The first thing that I want to do is let me just set the inequality as an equality. Oops, that's a 2 equal to 0. Now, let me take my numerator, let me take my denominator and see when are they equal to 0. So x minus 7 equal to 0. So it is 0 when x is 7. And for my denominator, x minus 3 equal to 0 and x minus 2 equal to 0. So therefore, I have x equals 3 and x equals 2. So now that we're done with that, we gotta test the points. So how do we test the points? Let's create some kind of a number line. So here we have our number line. And let's just plug the values that we got there. So we got a value. And I just noticed that I did a small mistake here. Because notice that when I distribute here 4x, that's definitely 4x. But 4 times minus 3 is not definitely negative 3. So let's just fix that. So this is actually negative 12. So instead of positive 3, this is positive 12. So if we combine like terms, this is not negative 7, but actually positive 2. So therefore, my numerator, it is not x minus 7, but it is x plus 2. Therefore, my numerator is not x minus 7, but actually x plus 2. So therefore, my numerator will be 0 when x equals negative 2. Sorry about that, but it's a quick fix. Nothing changes. Cool. So now that we have this, let's plot them in my number line. So I'm going to say that negative 2 is about here, positive 2 is about here, and 3 is about here. So notice that by plugging them in, I have created 4 different intervals. So let me just label them. Let's call this interval I1. Let's call this interval I2, this interval I3, and this interval I4. But before we test the interval, we have to test the points. So what's happening when x equals negative 2? Well, when x equals negative 2, my numerator, it is equal to 0. And notice that I had greater or equal to 0. So therefore, negative 2 will give me a true statement. So if it gives me a true statement, then on the number line, I'm not going to make it into a whole, but I'm going to be just filling the value because I need to take that value in consideration. So now what's happening at positive 2? Well, if I plug in positive 2 to the inequality, my denominator 0, that's undefined. So therefore, I don't want to take positive 2 as part of my solution, so I'm going to make it an open circle. And the same goes for 3. 3 will give me 0 in the denominator, so therefore it will give me an undefined value, so I don't want to take it in consideration. So now that we have created our number line correctly, let's test some of those intervals. So let's test the interval I1, which is the interval from negative infinity to negative 2, including 2, because we are not doing an open circle but a solid circle. Let's pick a value that is in that interval and see if it's going to give me a true statement. So I'm going to be choosing the value x equals, I don't know, negative 5. Well, let's see what we got there. Where are we testing it? Well, I'm just going to be testing it on the simplified version of this inequality, which is this expression. We could have tested on the original one, but I just can see that this is just easier to test it on. And they're equivalent statements, so I might as well just do it on the simplified version. And again, I want to see if it's going to give me greater or equal to 0, or pretty much a positive value. Well, if I plug in -5 on the numerator, we're going to have -5 times +2. So that's definitely a negative value on the top. And on my denominator, if I plug it in here, my first parenthesis, -5 times -3, that's definitely a negative value. -5 minus 2, that's definitely a negative value. So I'm going to have a negative divided by a positive, which is going to give me a result of a negative. So therefore, I can see that any value in this interval is going to give me a negative result. But notice that I just want those which are greater than 0, or those that are just positive. So this interval fails. So therefore, I cannot use the first interval as being part of my solution. And notice that in here, I'm just being a little bit lazy. I don't want to do the whole calculation. I'm just going to be looking at the signs, which that's essentially what we're doing here. We just want to take a look if it gives me a true statement. So I know that the first interval fails. So let's take a look at the second interval. Any value between -2 to +2. So for that, I'm just going to be choosing the value of 0. So let me just say x equals 0. And again, the second interval, it is from, open parenthesis, -2 to close parenthesis 2. Well, let's see what that gives me. Well, if I plug in 0 on the numerator, that's going to give me a positive value. So positive on the top. If I plug in 0 in the denominator, my first parenthesis is going to be negative, and my second parenthesis is going to be negative as well. So now if I simplify, I have plus, negative times a negative, it's a positive, and a positive divided by a positive, it is equivalent to a positive, which any positive value is greater than 0. So therefore, that's a true statement. So this is true. So let me just take it in consideration as being part of my solution set. So again, this is false, and this is true. And we're going to do the same for the third and the fourth interval. So for the third interval, which is the interval from 2 to +3, let's just choose an x value. So for that, I'm just going to be choosing, okay, it's 2.5. And let me see if it gives me a true or false statement. Well, if I plug in 2.5 on the top, that's going to give me a positive value, which is 4.5. I'm just going to care about the signs. If I plug in 2.5 on the first parenthesis here, that's a negative value. So I'm going to have negative. And on the second, if I plug in 2.5, that's going to give me a positive. Now simplify, positive on the top, negative times a positive, that's negative, and a positive divided by negative, this is a negative value. So therefore, this is false. So interval 3, we're not going to take it in consideration. And the last interval is from 3 to +infinity. So let's just test that. So the last interval, it is from 3 to +infinity. Let's choose a value of x. So for that, let me just choose 5, and let's see what happens. So if I take a look at 5, plug it into the top, that's definitely a positive value. Plug in 5 on the first parenthesis, that is definitely a positive value. Plug in 5 on the second parenthesis, that's definitely a positive value. Positive divided by positive, that is a positive statement. So therefore, this is true. And if it's true, then I want to make it part of my solution interval. So from 3 to +infinity is part of my solution interval. So now, finally, we have our statement. I know that my solution, it is going to be the second and the fourth interval. So let me just put them all together. So it is going to be from -2 to +2 union 3 to +infinity. And with this, it concludes our lesson for solving rational inequalities.